I want to show you a practical case. Well, we come back to the parallel plate capacitor. In the past, we somehow filled the capacitor with perfect dielectrics. But sometimes, in the real world, dielectrics tend to be slightly conductive. Okay, cannot be blamed. So what happens if this given capacitor is filled with two different conductive dielectrics? All that we know is the surface area of the plate is S, and we applied a potential difference of V. And we know the material properties. We know epsilon 1, sigma 1, epsilon 2, sigma 2. Then, are we capable of finding J, the current density, in the two materials, and E field intensity in the two materials? And is it possible that we actually find out the resulting charge densities? Remember, charge densities, I'm using plural. In this particular geometry or system, how many charge densities do you have? Well, you have the metal dielectric interface. As long as you have interface, you might have surface charge density. So you have surface charge density 1, surface charge density 2, and these are both metal dielectric interfaces. Easy to solve. But now you also have a third interface. This is across two leaky dielectrics, right? So remember, whenever you meet this type of problem, you have three different surface charge densities to be solved. But let's nail it one by one. We want to determine the current density, the field intensity, and charge densities. How should we start? Well, we know from boundary condition, J normal are continuous, right? And in this case, again, we can assume the two parallel plates are quite big as compared to the total distance. So all the E fields and all the current densities are flowing in the normal direction. So we don't have the tangential components, right? So J1n is equal to J2n. So basically J1n equals to J2n means the entire current is flowing smoothly, only in the normal direction, okay? So both J1n, J2n are equal. I have a constant current. So constant current multiplied by R1 plus R2. What is R1, R2? The resistance for the first material. R2, the resistance of my second material. Today, we already introduced how to properly formulate the resistance. Once we know the length, we know the area, we know the conductivity, we know resistance, right? So we can directly write down I times R1 plus R2, and that is equal to my supplied potential or voltage. But J is nothing more than current divided by the surface area. So this is straightforward. For this given problem, right, parallel plate, very big plates, you can just calculate the current density. Second, well, if you were asked to find the E field inside the materials, what you know is, well, E1 and E2 can be different, but basically they're all directed in a normal direction. But once you perform the line integration of E1 over D1 plus E2 times D2, the total potential comes up to V, right? So V has to be equal to E1 D1 plus E2 D2. Okay? Where is this coming from? This is actually coming from J, right? Because divergence of J is equal to 0 and J equals to sigma E, you know that sigma 1 times E1 is equal to sigma 2 E2. Okay? So somehow we can reformulate here E1, E2 using from the help of this equation. So you have two ways to formulate it, right? You can express E2 as sigma 1 divided by sigma 2 times E1, which is this case, or you can replace E1 by moving this downwards. Okay, so you have two ways to express it. And that's what you have. Voltage is given, right? Voltage is given, so you can quickly derive the results for E1 and E2. But the problem comes for the charge densities. Again, as I emphasized, we have three interfaces. So you have to properly formulate or evaluate all surface charge densities. Now the first one is quite straightforward. I mean, rho 1 is the surface charge density across the top metal dielectric interface. It's directly given by epsilon 1 E1. If you have problem knowing why rho 1 is equal to this one, this is really the time for you to go back to the boundary condition for E fields. Why can't I just write down this? D1n minus D2n equals rho, but because now I have the top material being metal, I assumed these metal plates are comprised of perfect metals. So inside the metal, you cannot have fields. Okay? All right? Rho 2 has to have a negative sign. Why? D1n minus D2n equals to rho, but now the bottom is now replaced by metal, so D1 is 0. So therefore, you have a negative sign. And this has to be negative, right? So if you add the two together, you might have charge cancellation, and you have to maintain charge neutrality. Okay? So these two simple formulas actually test your understanding to use n minus d2n equals rho s. Okay? For the top interface, D1 is in the dielectric and D2 is in the metal, so this one is 0, so you have positive charge. But for the bottom surface, bottom interface, so the top, this is dielectric and this is metal, equals to 0. For the bottom, you have metal where you have no field inside and you have the dielectric, so you have the negative sign. Okay? And the physical meaning is the top and bottom charge densities need to have different signs to preserve charge neutrality. Okay? All right. At this point, do we need to calculate this rho? The surface charge density across the two conducting dielectrics. Well, of course, I mean, you can calculate it, right? d2 minus d1 dot the surface normal, that gives you the surface charge. But if you calculate in this way, you are following the basic formula, which is fine. But is there a quicker way to do this? There's nothing wrong when you invoke this basic equation, right? There's nothing wrong. The difference of the two flux densities making a dot product to the surface normal gives you the right amount of charge density, which is fine. You already know E1n, E2n, so you know everything. But is there a quicker way? Why am I asking this? Can you tell me, does rho 1 plus rho 2 equals to 0? Let us come back to the simplified version of the problem. Let's come back to the two parallel plates. If the two parallel plates are filled with only one material, let's call it rho 1 and rho 2. Okay? If the parallel plate capacitor is filled with a single material, rho 1 plus rho 2 equals to what? Can any student watching the streaming tell me this answer? No one? I'm going to give you a choice. 0, not 0. Number 1, number 2. I mean, the filming crew and the TA can also raise your hand. Choosing 0, raise your hand. No hands. Not equal to 0, raise your hand. There's still no hand. That's a typical problem for Asian students. You just ignore the question. Think about it. We emphasized about charge neutrality, right? So the total number of charge needs to be maintained at 0 because you don't create charges magically. So this means when the parallel capacitor is filled with only one material, on the top interface and the bottom interface, they share the same strength of E field. Okay? And thus, rho 1 and rho 2 has to be equal in amplitude but opposite in sign. Right? If you have positive 5 coulomb, you have to have negative 5 coulomb so that totally there's no charge. And that's called charge neutrality. But now that the fact this capacitor is filled in this way, right? Top you have material 1, bottom you have material 2, and thus making your E1 and E2 being non-equal. And therefore, your D1n and D2n non-equal, right? So basically, rho 1 plus rho 2 does not vanish to 0. Okay? So if you have this filling, epsilon 2, epsilon 1, when you have two different fillings, I mean, rho 1 plus rho 2 will be not equal to 0. But charge neutrality still needs to be maintained. So that means you have rho Si. So rho Si is equal to rho 1 plus rho 2, probably in the negative sense. This is a quick and straightforward way to calculate rho Si. Of course, you can invoke this, conventional equation to calculate based on the fact E1 and E2 are different. But what I'm saying is, charge neutrality cannot be violated. So, rho 1 plus rho 2 plus your internal surface charge density still needs to be 0. Right? So once you can quickly formulate rho 1 and rho 2, rho 1 and rho 2 plus rho 1 plus rho 2 and take a negative sign, that is your internal surface charge density. And there is more deeper implication. What does that mean? What does that mean? Why charge neutrality has to be maintained? Let's try to relate to Gauss's law. Gauss's law tells me, well, if I form a closed surface, so if I am someone standing outside of capacitor, right? Divergence of D is equal to rho free. So if I'm standing outside, I have a closed surface encompassing the capacitor, so I'm outside. Charge neutrality tells me rho 1 plus rho 2 plus this internal surface charge density is always equal to 0, right? Due to this fact. So this is 0, meaning when I'm outside of the capacitor, there's no E field. Right? We assumed this parallel capacitor is huge, so all the fields are self-contained between the two plates. And therefore, when you're outside, you don't have field lines. You don't have field lines in the language of Gauss's law is when you're outside and you look inside, all the charges adding up inside the device has to be 0. There's no net charge. Okay? So that is actually a beautiful manifestation of Gauss's law. All right? So you have a quicker way to find rho Si. All right? Stop here, and we will come back on Wednesday. But on Wednesday, I will quickly sum up the electric current, and we will move into magnetics. Exciting topic. All right? See you on Wednesday.